Hi everybody, welcome back. So in this very last reaction, you guys are now going to learn in this chapter, and then actually probably for the whole semester, it's the last reaction we're going to learn for now. We are going to cut alkenes in half in a reaction which is called ozonolysis. So it's a pretty cool reaction. And just to introduce the reaction and the reagent a little bit, just want to explain to you again what ozone really is, right? We're going to draw the Lewis structure in a second. The molecular formula is just O3, so 3 oxygens all bonded together. It's a reactive molecule, it oxidizes other molecules, and you know it's in the air, right? First of all, the ozone high up in the atmosphere protects us from dangerous UV radiation. So you might have heard about the ozone hole right over the Antarctica, and that means you want ozone high up I think very high up in the atmosphere, and I think in the stratosphere. And so if you take away that ozone, you're going to get exposed to the UV radiation, which normally filters out. It gets filtered out by the ozone. Okay, but now at the bottom of the Earth, at the surface of the Earth in the air, the ozone is bad for us, and it gets generated by compounds called NOx, so that those come out of engine exhausts, for example, from cars, and they react with sunlight, and VOC, that's volatile organic chemicals, and plus sunlight, and that forms ozone out of the oxygen in the air. And so this ozone does this kind of cutting of olefins, this kind of reaction I'm going to show you, and that's bad for us. So if we inhale that, it can cause lung damage and bad breathing problems and things like that. Okay, so that's why I want to show you what ozone now does to our bodies. Okay, essentially what happens, it cuts this carbon-carbon double bonds in half. The process again is called ozonolysis. The LYIS, the lysis, right? That means cleave. Okay, you might have heard of cell lysis, and that also means you cleave cells. So ozonolysis means you're cleaving double bonds with ozone. And here's how it looks like. It's a process with actual chemical structures. So we start with an olefin, and you have a left part, the right part, and now you use it's a two-step reaction sequence. First, you have to put ozone there, just a gas. People generally use an ozone generator. It's like a machine which produces ozone in the lab. And then you use a reducing agent. The reagent I want you to remember, the most commonly used one, is DMS. DMS stands for dimethyl sulfide. So it's basically just a sulfide which has 2 methyl groups attached. Very simple compound. Okay, a sulfur and then 2 methyl groups on it. And that's just used in the second step. Yes, what happens is, essentially you cut the double bond in half, but then you have to put something where the double bond was, right? Because otherwise the carbon wouldn't fulfill the octet rule. You can't put hydrogens there. You can oxidize the compound, so you put 2 carbon-oxygen double bonds there. Okay, so again, here's the red part of the molecule, and then the right would be the blue part here. That's where it came from, and you see where the double bond got replaced with the 2 oxygens there. So ozone, you don't have to remember really the mechanism for this reaction, but I want you to at least remember the structure and the resonance structures of ozone. Okay, there's 2 resonance hybrids. Okay, here's how they look. This is one resonance structure of ozone. So you note the positive formal charge on the central oxygen, the negative charge on the other oxygen. But now you can push the negative charge from the right oxygen to the left oxygen. That gives you the other resonance structure. So the negative charge is actually equally distributed between the left and the right oxygen. So both of these terminal oxygen atoms carry a negative charge of minus 0.5. Okay. And I want to make a note here that you don't have to remember the mechanism. It's a very long mechanism for this reaction. Fills about a page in your book. If you're interested, again, I recommend you look at the book. If you have any questions, come talk to me. But you don't need to know this really complex mechanism for the exam. Okay, but you have to know this reaction, what it does. Don't need to remember it. Good, okay? Give you a few seconds to finish writing this. And next we're going to look at what I'm potentially going to ask for. Typical exam question on the final for this kind of ozonolysis. Okay? So we are pretty much going to we're going to look at so-called retrosynthetic analysis. But one more thing. I want to make a note here that see those two green oxygens have replaced the double bond, okay? And the carbon-carbon double bond was replaced by two CO bonds. CO double bonds, right? Never forget that. So now I'm going to give you a problem where we need to use ozonolysis. And we're going to do basically retrosynthesis here. And retrosynthesis means we're going to give you a product and I'm going to ask you how to synthesize it. In this case, we want to use ozonolysis. So I want you to provide the starting materials for the following transformation. The question mark is what you want to find out. And then we're going to do ozonolysis. That's ozone first, followed by DMS, red dimethyl sulfide, as we said. And the product I would like you to form of this ozonolysis reaction looks like this. Okay, it's a diketone. So I would like to give you about 5 minutes or so to think about this. Come up with a structure which, when you do ozonolysis, gives you this diketone. Think about it carefully. Kyle can also help you figure it out. He can walk around and give you some advice while you try it. If you want, you can try in groups of 2. Okay, we'll reconvene I'll give you the solution in a couple minutes. Thanks.